from the ERT, because it gives us directly a resistivity measure. And one way also to improve the inversion is to pre-compute the resistivity models instead of using the classical deterministic inversion. The big advantage of this technique is that we can also reuse the collection, of course, on other data sets. And if we need a specific, like we are working on a specific site, maybe we can just add new models to the collection with specific features that we know of. And this is still, it's definitely faster than the previous method. And it's also more stable. So that was it. Thank you for your attention.
Thank you, Nicola. Other questions? No.
Grazie.
No. Ok, passo avanti. Ok. Sì. Okay, the second presentation is mine. Low-cost geomatic surveys for emergency intervention on cultural heritage, the case of historic U-Wall in Cagliari. Okay. Okay. Good morning. I'm Giuseppina Vacca, and I'm from University of Cagliari. Come faccio da Oh, buongiorno.
Ok, ora va.
Va? Okay. My work is about a study of new low-cost technologies for the cultural heritage geomatics survey to create a 3D model. And among these, we want to identify the fastest ones for a quick survey with a good accuracy. The documentation and the metric knowledge of the cultural heritage is very important. And it's becoming crucial if we consider the state of the degradation of the major part of the cultural heritage. So our study is inserted in these topics. For 3D model cultural heritage, different techniques are used. For example, multi-image photogrammetric or terrestrial laser scanner. But in our study, we studied different techniques, low-cost techniques and fast technique. And since 2020, one laser scanning sensor was implemented in the Apple devices like iPhone or iPad Pro. Okay. The technical specification of this sensor that Apple recommended it mostly for augmented reality or virtual reality is not available. But from the scientific literature, it seems that it consists of a solid state leader. In this picture, you can see the iPad that we used and the app that we used for the survey of the cultural heritage. The use of the Apple LiDAR sensor is possible only through the app that can be download from the App Store. And this app can be in different format, or free of charge version or a paid version. In this study, we used a Polycam app. Okay. Different research demonstrated that potential and functionality of both sensor in their phone or iPad, and of some app like Setscape, 3D Scanner app, or Everypoint. Accuracy are investigated in different relevant scenarios, such as indoor or outdoor, static or dynamic configuration, and also for different type of cultural heritage, for example, statue or decorated rooms or external facade. This research that I present to you is part of this study about low-cost geomatic methodologies for the survey of cultural heritage. In particular, we are studying two low-cost methodologies: close-range photogrammetry. Low-cost close-range photogrammetry is like multi-image photogrammetry with structure from motion approach, and survey with Apple LiDAR sensor. And in particular, we focus on the case study of a perimeter wall of a historical building in Cagliari. This wall is the perimeter of the Institute of Normal Human Anatomy of the University of Cagliari. The perimeter was length about 43 meters. And for our study, we choose two parts of this wall. On the left is the part one, made of stone without plaster, and on the right, the part two, plastered. And it is the most compromised, so you can see the iron structure to support the walls. The survey for 3D model was performed with the close-range photogrammetry and the Apple LiDAR sensor with the Polycam app. The wall also surveyed with terrestrial laser scanner methodology for the validation of the two surveys. For the terrestrial laser scanner survey, we used the Faro Focus 3D terrestrial laser scanner that you see in the picture. It is a compact laser scanner, especially for the cultural heritage or building, because it has a range between 0.6 and 120 meters, with error about 2 millimeters for scanner object that the distance is between 10 meters and 25 meters. We made 4 scans for all wall, and with the scan made a resolution of 7 millimeters for 2 meters of the distance. In this slide, you can see the point cloud from terrestrial laser scanner for the part 1 and part 2. For the part 1, the point cloud, the point are about 7 million, And for the part 2, the points are about 9 million. The second survey we did is the Apple LiDAR sensor with the sensor insert in iPad Pro with the Polycam app. In this slide, you can see the point cloud for the part 1 and the part 2, and you can see the number of the point cloud, 500,000 for the part 1 and about 3 million for the part 2. It's very different, the number of the point between terrestrial laser scanner and the sensor, Apple LiDAR sensor. The last survey we made with the close range photogrammetry, low cost close range photogrammetry with amatorial camera, digital camera. The camera was Canon EOS M3, sorry, and we used Metashape by Agisoft for the processing, for the image processing. For the part 1, we took 66 images, and for the part 2, we took 55 images. All images have been elaborated in medium mode with Metashape software. Also in this slide, you can see the point cloud for the part 1 and the part 2, and the number of the points, about 2.5 million for the part 1 and 4 million for the part 2. Okay, for the validation of survey point clouds from LiDAR sensor, Apple LiDAR sensor, and close range photogrammetry, we use the cloud comparison software, especially using cloud-to-cloud distance tool. Cloud-to-cloud calculates the minimal distance between every point from the two point cloud. So in this slide, you can see the result for the compare close range photogrammetry and terrestrial laser scanner. In the table, you can see the deviation standard is about 4 centimeters for the part 1 and 3 centimeters for the part 2, with a mean about 6 millimeter for the part 1 and the part 2. So it's a good results. For the compare Apple LiDAR sensor and terrestrial laser scanner, in this slide you can see the results. With a deviation standard about 4 centimeters and 4 centimeters both part 1 and part 2, and with a mean about 5 millimeters for the part 1 and 1 centimeters for the part 2. At least Apple LiDAR sensor and close range photogrammetry compare. The table, you can see the deviation standard 3 centimeters for the part 1 and 12 centimeter for the part 2 with 5 millimeters mean for the part 1 and 6 centimeters for the part 2. This compare is not very good, but 12 centimeters is a good for the fast survey for the cultural heritage. So in conclusion, from this result, we dare to assert that online with other research, both close-range photogrammetry and Apple LiDAR sensor can be a tool for 3D models, creating of cultural and cultural heritage. But when I use the Apple LiDAR sensor, I know that the range of this sensor is only 5 meters. This sensor survey only object, room, or asset for with a range only 5 meters. And this limitation cannot permit to survey a big asset or big building without more scans that must be joined. So this is very limited of the this Apple LiDAR sensor. It's all, and thank you for your attention. I pass the time. Thank you, my colleague. There are a question? Yeah.
The limitation of 5 meters is related only to the free version or both for free and paid version?
For all, yes, because it don't depend about app, but the sensor in iPad or iPhone. Okay, thank you so much. We are on time, and
Sì, vediamo se si sono collegati.
the presentation is a GEO Advanced Citizen Observation for Atlantic Geohazard Risk Management. The speaker is Eleni Manghina.
Non si è collegato nessuno.
Okay.
Yeah, that's great. Okay. It's ready. 15 minutes, yeah? Yeah, okay. Hi, everyone. Although my name is Greek, I come from Ireland. I've left Greece in '97, so I'm delighted to be back home and presenting our work on AGO. It is a citizens observatory. It's funded from Interreg, and we created a citizens observatory for Atlantic geohazard risk management. The names are our postdoc, Levent Gorgu, Kieran Parker, Christine Lemon are from Northern Ireland for one of our 5 pilot studies, and our earth science is Professor Owen Holohan. So what I want to give you first a brief information about the project itself, then the Citizens Observatory. You can use your mobile phones with your QR codes. It's open source. You can all use the platform and the mobile apps. And I just want to show you what we have been doing differently compared to other projects. But first of all, the total budget was EU contribution of 2.4 million, and our priority was to strengthen the territory's resilience to risks of natural climate and human origin. We've all experienced the climate change, and there is a lot of disasters happening around the globe. And we wanted to strengthen the risk management systems within municipalities, within the different territories on the North Atlantic of Europe, because INTERREG applies the project in this area. So you can see here from the map, you can see here all the Northern Territory, including Northern Ireland, down to France, Spain, Lisbon, Portugal, and all this side here. And you can see the different partners that we had. So we had interdisciplinary consortium, we needed that, and we needed the stakeholders to use the platform. And as you will see, we used loads of public services in order to connect with the platform. So just a little bit of background. I don't know if you're familiar with Citizens of Science observatories. First of all, we have an evolution. The first definition was given in the 90s when we wanted to open up science and we wanted the scientific citizenship to come on board with the researchers. In the USA, projects in which non-scientists, such as amateur bird watchers, voluntarily contributed scientific data. This is where it started in the 90s. Then in 2013, we had the general public engagement in scientific research activities. And then 2014, about scientific work undertaken from the public. Because with IoT, everybody is accessible and we can take data from the public and different observations. So in terms of research projects, the Citizen of Science is emerging as a new form the last 10, 15 years. We have interactions between scientists and citizens, and we can assume many forms. Sometimes it's voluntarily involved. Sometimes they're constituting a major change in the way research is conducted. And it opens up new possibilities. And you will see what we have done in this platform. Also, the educational and engaging value is of high importance for these projects, and it's dependent on the public. So it's a community-based geohazard monitoring and information systems. What we do is we build upon the Earth observation observatories, what we're taking data from the satellite, and we embed them in portable or mobile personal devices. The citizens then, by using their devices, they can engage and they can help in the data acquisition and knowledge acquisition of what's happening in the environment. So as a state of the art, there has been a study there from the Finnish Environment Institute, and there have been 69% of the identified world observatories have an environmental goal. And the most common goal that these observatories have is the participatory, in which citizens are actively involved. The top three stakeholders are the citizens, the academy, which is the researchers, and the government and the nature enthusiasts. What are the techniques that we're using? Data benefit, interest from the citizens, and of course, unify all these within the same portal. And there is a clear trend of dematerialization of the observation submissions. So we saw 38% web-based applications, mobile applications 23%, and technologies that collect data only 2%. So we are actually targeting this collection of data. You will find lots of observatories, but there is not many that are collecting them. And I just included this slide. I'm sure the slides will be available. If anybody wants to do any literature review, these are the examples that have been launched around the world, and now AGO is included as well. So within AGO, we have the scientific community, we have the citizens, and in between we had 5 pilots. One in Canary Islands, and that had to deal with rock falls. Brittany, France, coastal risk. Northern Ireland, pit slides. Lisbon, multi-hazard. And we had the Northern Ireland for pit movements as well. So we created a cooperation in order to have the Atlantic geohazards risk assessment to help with preparedness before the disaster mitigation and prevention. And we delivered 5 solid case studies to improve these risk management systems. Also, we encourage the regional level uptake and the use of these products and services. And these are the partners involved, and we gathered observations for hazard prevention. As you can see, partners from Spain, Ireland, UK, Portugal, France. And the observatories are a phenomenon. The information system is dedicated to collect the data. It's community-based environment monitoring. But the main problem so far with existing systems is that previously we had complex observatories. This is very simple, very user-friendly. We use the UX design approach. I'm from School of Computer Science, so I focused more on the development of the platform and the apps. But when we did the evaluation, it was an agile process. So we always got feedback from the municipality, so we knew what we were developing. So enabling technologies that are ready to use and gather the right information is the key. And the geohazard experts, they had to define the data that we needed to collect. Also, the user interface and UX experts, they were very helpful in terms of actually having an easy interface for the users. So UCD did all the development of the platform and the pilot mobile apps. And in terms of architecture, just to give you an idea of the complexity, we use the MISR toolbox. This is the toolbox that right now is written in MATLAB, but we plan to rewrite it in Python, where we collect all the data from the satellite. There is a server, and then we have the AGO platform on the server as well, and we are able to visualize the data from the satellite. Again, you can see here the different components in terms of forming the geohazards catalog and have an output in the INSAR toolbox. So this is our platform. If you are on the desktop, you can use the agoplatform.eu, or I'll show you the QR codes if you want to use the actual mobile apps. So you need to log in, you need to create a profile, and then you can see that you can add the different events of what is happening. And also you can upload when there is a disaster, a photo. So let's say somebody is in the mountain, very simple, they're uploading the photo, and then this passed on the Citizens Observatory, and then the municipality. It saves time instead of somebody going to observe. The citizens are helping with this. Event types, what we have currently is tsunami, earthquake, rockfall, sinkhole eruption, landslide, river flooding, marine flooding, coastal erosion, building settlement, and wildfires. So all these, then you have to add all the data, for example, whether people are at risk, are animals at risk. So there is a lot of metadata that somebody can fill in and inform the services. It's a map-based interface, so the web interface is like that. It picks up your location from GPS, and then you start uploading the data. Now, there is a profiling system as well, where only the managers can download the data, and these are the people in municipalities. And then what we have done is they're connected with emergency services, so the fire brigade is informed, so the right services are informed. And they can be downloaded in different formats, JSON, Excel, or CSV. And then sometimes people might put up data or photos that they're not really emergencies, so they can approve, reject, or archive the events. Also, the managers can draw polygons through the site, and they can select events. And we have added educational content both on the web and the mobile version, and it's available also offline on mobile for emergency. So if you click on the 3 dots, you will see them once you get your mobile app. Then you can get informed about this type of disasters and how you can react if that happens. So if you click earthquake, it's telling you what to do and what to do when you're indoors or outdoors, and follow up. There is a manual. You can view the manual step by step. Okay, and you can actually download either the Android or the iOS. Is there a question or is it just no? Okay.
So we have to download
The app. Yeah. You cannot? Oh. Can you download?
Yes, that's true.
It's downloading. Are you having an iPhone? Can I see? Ah. Yeah, you have to download the test flight and then the app. Yeah,
okay.
But once you download it, you will see that you can select an event type, the type of settlement, and the observed damage, for example. And what we have managed, somebody's, yes, you did it, yeah? Yeah. I'll see on my apps I'll go on the drive and see why because mine downloaded this morning.
Use code.
No.
Can I try other?
Did you do it with your camera?
No. Test flight.
I'll see
Okay.
Apple Store.
Okay.
Why? Because it was
But
okay.
the name?
AGO.
Okay. C'è qualcuno collegato, Rossella?
Sì, si collega.
I'll go to my Apple Store and see why not.
Did you finish?
No. So, just a couple of pictures to show you. This is in Madeira, the rock falls. This is in Ireland. This is flooding. I think it's Madeira as well. And this is in Lisbon. You can see the cracks in houses. So people start observing and they're uploading. And in terms of reporting, you can see that you can go capture with camera, or if there is a gallery and somebody else has already posted, you can add to their post as well. So for example, somebody in the landslide here has put a photo and somebody else has added the other photo. So all these are live and instant so that services can get fast. Also, we have a shareable event details. So if, let's say, some services don't have access to the app, then we can share the event details and they can find them. And that's around the globe. The app is for everywhere. It has been used already in India, for example. That's why. And there is a quick monitor as well. where you can click and add the event. And again, the event is Cerebral, the user manual. And in terms of the INSAR observations and the INSAR toolbox, we have created one that actually manipulates the data from Copernicus. So you can see here, and you have the same in the paper. You can see 3 observation sites here, Northern Ireland, Lisbon, and Madeira. And we have taken the INSAR data and we have analyzed them. We have used Sentinel-1A and B, SAR satellite, with a data time span from 15 to 21. And you can see here the main mode of the data. So the main products are, we have the ground displacement velocity field and the ground displacement time series as well from the data we collect. In terms of the user interface for the INSAR toolbox, we have done some developments, and you can see how somebody can prepare the SAR data, you can do the processing and the time series analysis on a web-based application. You have the different bars, the information box, and again, you have the stamps processor and the MinPy processor here too. Now, the provision of the satellite-derived data, and you can see it here, that's the sample from Google Earth on the test site at the volcano. You can see the long valley of the caldera, and the rectangles are the coverage of the regions of interest. The red dash around them are the caldera boundary, and the other boundary in here is the LVC. And the solid blue line is the outlines of the resurgent dome. So actually researchers can further analyze of what has happened live. This again, the Northern Ireland AGO pilot, that's the Causeway Coast. Has anybody been to Ireland here? Yeah, have you been to Causeway Coast? Okay, and we can see the maps and analyze of what's happening in terms of the rockfalls. Yeah. And again, the Garon point, you can see the long-term subsistence, the clear seasonal signal, and the peatland deformation. And what we do is we download the time series and we are able to analyze the impact that it makes. And that's the data from the Giant's Causeway. And as you can see, there's no evident deformation detected of the coast region, but some points can show noisy displacement time series, and these are of interest. So we have the ground surface deformation, we find the hotspot of deforming areas, and then we make the geohazard mapping. And how the INSAR observation is used, we're doing the evaluation process, and the small deformations that are noted from the data can be carefully interpreted from the experts. So we have developed a toolbox that's very easy to use. It's processing from row level satellite data to multi-temporal displacement analysis just in one flowchart. First, we have the interferometric synthetic aperture radar scientific computing environment. That's NASA's Jet Propulsion Laboratory. Then we're using the Stanford method for persistent scatterers. And finally, the Miami INSAR time series software in MinPy, which is in Python. And this is the actual interface of the INSAR toolbox. And it's free actually on GitHub. Let me know if you're interested. And we have also MATLAB interface for easy INSAR, the document itself that gives all the details where to download the toolbox itself. So we did 3 study sites for the INSAR: Lisbon, Madeira, and Northern Ireland. And this is my last slide. As a result of this project, we have 5 citizens observatories covering geohazards of all these 5 pilots. We have delivered information leaflets. You're free to download them from the website at ageoproject.eu. We have had several conferences, a platform that it's free to use. We have evaluated the observatories, and I'm looking forward to use it globally now. So I will be applying for funding in 2024. So if you're from regions that you think that are relevant to disasters, more than welcome to contact me, and we can see for further partnerships. Yeah. Any questions? I think I'm on time. Thank you.
Just to you, the app is very, very interesting, very useful, and it is it can be used for several purposes. Besides the risks. Just curiosity, do the data are available for researcher or can be downloaded from researchers or other people, or are only for the project?
At the moment, they're for the project. We just finished. So September is the final evaluation from Interreg, but I plan to download the data and put them on Zenodo. Okay. So it's open source data sets. Yeah.
It could be very interesting to start a collaboration or cooperation to apply your app to other region, for example, Sardinia.
Absolutely. And in other applications, for example, in agriculture.
Yes.
Yes.
Yeah.
Forest management, yes, exactly. And the flora, to monitor the flora changes over the years and the impact of climate change. I'm doing another project. It's funded from Science Foundation Ireland, and we are monitoring the waterlogged barley. Barley is our major plant in Ireland. I don't know if you have heard. So it's one of the major plants. So barley, because it rains differently now from climate change. It rains a lot in short periods of time. So we need to identify this phenotype of barley that is authentic. So it actually can support itself under these waterlogged conditions. So we're doing, I think, around 150 phenotypes at the moment. So we have around 7-8 acres of land, and we have planted the phenotype, and we're using drone data, but it could easily be with an app like this and satellite data for the farmers to see how,
I have a curiosity. How many users use this platform?
Well,
at the moment,
the moment, I need to check.
In your database, how many?
I haven't checked lately, but it was hundreds before when we had the meeting in Lisbon. So, but now it's open, so I'm sure there is more and more. Yeah.
Okay, very interesting.
Thank you. Thanks.
Next presentation is Luca Pirotti, Evangelisti.
Good morning.
Good morning, Azzurra. Sebastiano D'Amico is there? C'è solo lui. Ok, Azzurra.
I'm sorry, but my camera doesn't work.
Okay. Can you condivide your presentation? O ce l'abbiamo noi?
No. Yes.
Okay.
Just a moment. Let me know if you can see my presentation.
Okay. Okay. It's perfect. Okay.
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 Good morning to everyone.
At the moment, Azzurra, Azzurra?
Yes.
A moment, please.
Okay.
The next presentation, probably also the last, is transportation infrastructures exposed to seismic risk. Evaluation of social cost for resilience design. The speaker is Azzurra Evangelisti. Please, Azzurra.
Thank you. I'm Azzurra Evangelisti, and I'm a research fellow of the University of Cassino and Southern Lazio, and I'm a co-author of the paper cited before. The presentation is composed of a brief introduction on the damage caused by the seismic event, and particularly caused by liquefaction. Then risk assessment related to the seismic liquefaction phenomenon on the road transportation network will be presented. And finally, the preliminary results of its application on an Italian case study will be summarized and commented. Several events worldwide occurred have shown that the effects of the liquefaction phenomena, which is a consequence of a seismic event, can be very destructive. For this reason, it's crucial to estimate the potential losses induced by liquefaction phenomena in order to improve prioritization process. In the past 2 decades, significant efforts have been performed to develop different methodologies for estimating the potential losses induced mainly by earthquakes. And in the table are summarized the main research projects or methodologies proposed during the past, and as it's possible to see, only some of them performed the transportation analysis to evaluate the post-event scenario. It is worth to be highlighted that different transportation network analysis types are available. From the simplest to the most complex, we can find the vulnerability analysis, which according to a specific post-event scenario is related to the damage level of each single component of the transportation network, as bridge or embankment. The connectivity analysis, which evaluate the accessibility to specific or strategic areas despite the loss of service of some connections. The capacity analysis, which related to the network capacity to accommodate traffic flows, provides direct and indirect losses due to the damage level occur on the whole network. And finally, serviceability analysis, which take into account both direct and indirect impacts on the economic sector, provided a more realistic estimate of total loss on a long-term period. For the following case study, the capacity analysis, which represented a minimum requirement for guaranteeing reliable results in terms of socioeconomic impact related to the traffic flow rearrangement on the network, will be used. The liquefaction risk assessment methodology here proposed can be expressed as a synthetic formal equation where there is a combination of hazard, vulnerability, and exposure. Regarding the liquefaction hazard, the necessary factor for the occurrence of liquefaction are the seismic event, the presence of sand with limited fine content, the low density, and the saturation. As far as the road embankment vulnerability assessment is concerned, the synergy classification for the definition of the damage state limits has been adopted. And in particular, three levels of damage states are identified by means of three different levels of permanent ground deformation, which correspond to three different road network serviceability levels, from the reduction to speed to a complete road closure. Finally, the concept of exposure, which is expressed as the quantification of the socioeconomic damage that a community can suffer, it is strongly related to the evaluation of the social cost, which in turn can be defined as all the social and economic losses affecting a community after a catastrophic event. In this study, they have been evaluated by means of the total delay cost as a consequence of loss of serviceability of the transportation network within a capacity analysis. And in order to evaluate the overall social cost within a specific analysis area, the total delay cost has to be multiplied for the overall amount of days needed to bring back the transportation network to the pre-event condition. The case study that I'll present is in Italy, in the Emilian Po Valley, which in 2012 has been subjected to a series of severe seismic events that have caused a total of 27 victims, around 400 injured, more than 15,000 displaced persons, and extensive damage to the cultural and economical heritage of the area. Here, due to a particular condition of the subsoil, widespread liquefaction phenomena have been occurred, in particular along the municipality of San Carlo, Sant'Agostino, and Mirabello, along the old riverbed of the Terre del Reno River. The greatest concentration of liquefaction evidence has been observed. According to the liquefaction hazard assessment previously presented, the coupled approach for subsoil and infrastructure responses has been adopted. In particular, the Karamitros formula has been adapted to compute the liquefaction-induced settlement of embankment of Terre del Reno. In order to apply a probabilistic approach, four increasing seismic events have been simulated on the road network damage evaluation, in particular return period of 30, 50, 475, and 975 years, adding the back analysis case. The minor and the major seismic events are reported here with the damage level and the corresponding road network serviceability. As we can see, minor damage corresponds to speed reduction, moderate to an alternating one way, and the extended damage is related to a closed section. In order to evaluate the social costs suffered by the Terre del Reno territory, the travel demand forecasting model of Terre del Reno has been developed. Terre del Reno is characterized by a prominent presence of through traffic, which can affect the study area dimension. So after a sensitivity analysis, it has been identified a study area of 60 kilometers of radius. So in a buffer area of 60 kilometers of radius around a rural area located in the district of Terre del Reno, the travel demand forecasting model has been developed and calibrated. In particular, the origin destination matrix has been preliminarily developed based on the commuter mobility data derived from the 2011 census promoted by the Italian National Institute of Statistics called ISTAT, which contains only systematic commuting data. Finally, the origin destination matrices have been calibrated with traffic counts provided by the Emilia-Romagna region, and it is the satisfactory result. As it is possible to see in the summary, as the seismic intensity of the event increase, also the traffic delays suffered by the community increase. But In the last two analyzed return periods, a reduction in terms of both traffic daily and the relative aliquot of the social cost is highlighted. While it may seem counterintuitive, the reduction is correctly correlated to the damage suffered by the road network. In fact, in the last two return period scenario, the complete isolation of the municipality of Terre del Reno occurred. So in these particular cases, a considerable number of trips which generally take place in the territory of Terre del Reno are suppressed. These lost trips are also a cost suffered by the community, which must renew the movements of its normal everyday life. So, in order to assess the aliquot of social costs, which reflect the overall number of trips lost, the indirect losses due to the isolation of Terre del Reno should be evaluated. To conclude, a seismic liquefaction risk assessment of a road transportation network has been performed, and the strategy here proposed includes the assessment and the combination of the territorial distribution of risk, vulnerability, and exposure, also through geoinformatics. The strategy has been applied on a road system of Terre del Reno affected by a severe earthquake in 2012. Then the capacity analysis of the road network has been performed with the aim to evaluate the effects of the loss of functionality due to the liquefaction event. The results obtained, according to what is expected, confirm that as the seismic intensity of the event increases, also the traffic delays suffered by the community increases until the isolation of the municipality. In this case, the number of suppressed trips lightens the pressure on road traffic on the network, but at the same time, it causes increasing social costs paid by the community, which should be evaluated as indirect economic costs due to the isolation of inhabited and or industrial business center. Thank you for your attention.
Thank you, Azzurra. Other questions? No? Okay. We are finished. Thank you. Thank you, Azzurra.
Thank you. Bye bye.
Thank you, everybody. Yes. So enjoy coffee break.
Che era le 11 adesso. Le 11 greche.
Se io sono quella prima, che figure di merda. Ma perché non è andato? Non è mai andato. Sta aperto.
Cazzo dove?
Ok. Ok. Ci ascoltano?
Sì.
We can start. Noemi è collegata. Ok. We can start. Good morning, everyone. We can start with this workshop for named Geomatic for Resource Monitoring and Management. We have 4 presentations related to geomatic aspects of monitoring and manage the territory. And so we can start with the first one. Noemi Pagano is the presenter, but the title of the paper is Integrated Use of Geomatic Methodologies for Monitoring and Instability Phenomenon. The authors are Noemi Pagano, Alberico Sosnessa, Federica Cotecchia, and me, Eufemia Tarantino. Noemi, you can start with your presentation. Thank you.
Thank you. Good morning, everyone.
We are just trying to share the screen. Just for one moment.
Can you see?
Okay.
Okay.
You can start, Noemi.
Thank you. Good morning, everyone. I'm Noemi Pagano from Polytechnical University of Bari, and I'm just to talk about integrated use of geomatic methodologies for monitoring and instability phenomenon. The Italian peninsula is particularly subject to instability phenomenon. The study developed by ISPRA estimates that about 94% of Italian towns are subject to critical events such as landslide, floods, and coastal erosion. The impact of landslides in Italy is incredibly significant, thus representing a real social and economic problems. Risk mitigation strategies helping to avoid a disastrous development of an instability or support the emergency management phase of the event encompass a deep knowledge of the phenomenon to better understand its evolution to accurately monitor its effect. We can apply many methodologies identified according to the magnitude of the phenomenon, extent, and the accessibility of the study area. In this context, geomatic monitoring plays a key role through airborne satellite and ground-based technique. In the present work, the multi-temporal satellite interferometry technique and structural monitoring sensor have been employed. The investigated area is located on the border of the Apulian region. The landslide phenomenon threatens the northwestern sector of the urban area and also involves a zone called the Croyon Spring, located on the northwest of the historical center. The INSAR technology uses the phase information recorded by the sensor to measure the distance from the sensor to the target. When at least the two observations of the same target are made, the distance with additional geometric information from the sensor can be used to measure changes in the land surface topography. These measurements are very accurate up to the centimeter level and can be used to identify areas of deformation of the Earth due to critical events such as landslide, earthquakes, eruption, and eruption. The interferometric dataset used in this work was acquired as part of the European Copernicus program by S1 Sentinel constellation. Due to the variable orientation of the building-up area and the retaining wall north-south, almost perpendicular to the line of the sign, and the direction of the steepest path of the slope below the instability zone, the study area was analyzed from the data obtained along the descending orbit from March 2015 to April 2021. The map of average displacement velocities calculated along the loss shows that the PS belonging to the settlement area are the most affected by the instability, which is the active retrogressive scarp at the head of the landslide. Scatterings belonging to the cryo spring are also displayed. A simple filtering process has been applied to the historical time series. In this picture, the displacement average velocity map are shown with all PS belonging to the dataset and the DPS characterized by a filter coherence. To pursue a more trustworthy analysis, the PS with a coherence value less than 0.6 were discarded. The evaluation of the ground motion map brought out several classes characterized by a comparable behavior in terms of average velocity. As described in the cited paper, the PS trend is marked by a strongly non-linear behavior, with some periods characterized by a relative low velocity and other short periods affected by a higher velocity. These trends have been compared with the data downloadable from the EGS portal. The selected points are nearly the E and F points and with a coherence value greater than 0.6. They have been undergone to the simple filter and confirmed the particular behavior. To investigate the spatial and time evolution of the phenomenon, a more refined analysis has been conducted. The entire dataset has been split into 3-month temporal intervals with the purpose of evidencing possible remobilizations of the same portion of the unstable area in different periods. The back analysis highlighted that the whole unstable area is simultaneously involved in the acceleration phase, during which the average velocity has a sudden increase. The impact of the ground motion on a building is generally limited when the displacement affects the entire structure at the same time. In this case, there was a differential displacement at the structure-soil interaction level that produced the effect shown. The most impactful effects are located on the border between the stable and the stable area. In September 2021, 8 biaxial tentmeters have been installed on the containing structure to provide high-frequency monitoring of the wall and a prompt alert in case of a sudden change in its inclination, indicative of an acceleration of the instability process. The observed data were processed using a moving average over a range of 24 hours to minimize the effects of a daily temperature fluctuation. On the long period, the tintmeter recorded a direct or inverse correlation on the temperature. Maybe it could be related with the exposure of each one. Between the end of January 2023 and the end of February 2023, fast changes in inclination were recorded to the C2 channel by C03, C04, C07, and C08 tintmeters. The duration of this intensity variation seems to confirm the evidence of the MT-INSAR analysis, with periods typified by small displacement and phases with higher magnitude. In conclusion, the measurement acquired by the tintmeters that consisting the early warning system implemented after the MT-INSAR analysis evidence confirmed the particular trend of the phenomenon and highlighted particular zone of activity. The outcomes of this work provided key information to the structures responsible for the management of the risk connected with the instability, and allowed the addressing of the proper design of the mitigation works. Future development of this study foresees the analysis of ground topographic observation regarding the slope area underneath the town and the integration with the geological and geotechnical models to gain a comprehensive understanding of the landside evolution. Thank you for your kind attention.
Thank you, Noemi, for this interesting presentation. Someone would ask something to Noemi? Nothing? I would ask to Noemi if in the future are you thinking about to forecast analysis, provisional analysis for the management of this situation? I know that you are thinking to have more observation on site, but for statistical analysis for the management of the situation for provisional forecast analysis.
Yes, it should be very, very important to forecast a disease like this, so we can implement this technique, and also we can apply also a previsional system to this. But we need more data to do this.
Yeah. I guess. Okay, we can continue. Thank you again, Noemi Pagano from Polytechnic University of Bari. Okay, the second presentation and the second presenter is author is Cristina Monterisi. Cristina Monterisi with Alessandra Capolupo and me, Eufemia Tarantino. We wrote a paper, a work titled Crowd Sensing Close Range Photogrammetry for Accurately Reconstruction, a digital twin of a cultural heritage building using a smartphone and a compact camera. Please, Cristina, you can start.
Good morning to everyone. I'm Cristina from Polytechnic of Bari, and today I present a work called Crowd-Sensing Close-Range Photogrammetry for Accurately Reconstructing a Digital Twin of a Cultural Heritage Building using a smartphone and a compact camera. Photogrammetry... Lo schermo. Thank you very much. Ok, se no... Ma non è condiviso con gli altri? No, ogni volta bisogna condividerlo. Okay, I'm sorry for the inconvenience. Photogrammetry ensured the possibility to have accurate reconstruction of 3D model of cultural heritage according to the preventing and directives of European Union about preventing and digitalizing of cultural heritage. In this field requires a role key by crowd-sensing photogrammetry because the researcher in this field is working to reduce the cost of the sensor for acquiring data, but also to maintaining accuracy of the reconstruction model and to reduce also the time of acquisition and processing of the data. So crowd-sensing photogrammetry with smartphone and compact camera could have an important role in this field. Many researchers studied the importance of crowd-sensing and close-range photogrammetry, but a few researchers work on the comparing compact camera and smartphone technology and accuracy of reconstruction of the model that are very cheap sensor and user-friendly sensor. All this work have a focus on small objects. So we in this work decided to study a big target, the church of Ognissanti in Valenciano, chosen by for its importance, historical importance and architectural importance, but also with the complexity of the context that's surrounding this church, because this area is surrounded by a lot of olive trees and a lot of dry stone walls, so have more complexity to the reconstruction and the acquisition at the site. We can see there the workflow of the project of the work, the aim, that become from a dataset definition from smartphone and compact camera. We acquired 1,052 images from one sensor and from the other, and the planning of survey from the pre-processing that we made with the open source platform UCMAC for its importance in is a very powerful tool also for calibration phases. And in the processing phase with the cloud cleaning, before with the manual cleaning, and then by applying filter in cloud compare to be the computation, to arrive to the computation of cloud to cloud distance and to the statistical analysis. Okay. In the survey, in this table, we can see the specific of utilized camera, and the survey was planned to have the possibility to compare data from different sensors. So to maintain the dimension of the pixel, we calculate the different acquisition distances from the object, from the target, maintaining the same horizontal distance photo, because we have this problem of a lot of trees and a lot of dry stone walls. And the survey was planned to be in only one day, with weather condition homogeneous, wind and meteorological condition homogeneous, to have the possibility to compare that. This is the Church of Ognissanti. In the results, we can show the type points maintained in image matching during the block bundle adjustment phases, like in a sort of error matrix. We can see that between the 1,012 images, the 89 images have a image matching more than 99% of type points. So it's a very interesting result. And at the bottom, we can see this graph that are only a little extraction from all the graphs, because we took 15 images for sensor, and we studied the average residual in function of iteration number in image matching during the block bundle adjustment phase, dividing that from the percentage of tree cover. So we have an example of image with the more image paired. So smartphone in the red line and compact camera in the orange line. The first is for more than 80% tree cover, and the other from 15 to 18. And we can see that we need a lot more time, more interaction to have a similar results with the smartphone respect with the compact camera that is more faster to have acceptable values about average residuals. But after 20 or 30 iterations, we have similar results. In this table, we can see that the dense point cloud of compact camera is 3 times denser than the smartphone reconstructed dense point clouds. Also because is confirmed in literature, this also with the small object, so is confirmed also for a big target. We have then to co-register the in cloud compare the 2 clouds to have a comparison of the reconstructed model, of the accuracy of reconstructed model. And we found that the point cloud's average distance was like 0.01 meters. So instead of the difference between application times, processing times in smartphone and camera, we have not so far results from one and the other method. We have the more differences in the top of the building, because the smartphone survey was more near the building to maintain the dimension of pixels. So put not so in the top we have the main differences. And so to conclude, we can see that smartphones can be used to collect in situ data, because it's a simple way that everyone have to together. And I used a smartphone, very commercial smartphone, not a big one, also to prove that important results can be obtained also with very low phases smartphone, and require more time, but the results are interesting. And given the difference of flexibility and processing time, we are so that the combination of a compact camera and radial extended, that is the calibration algorithm, is the optimal solution. And MICMAC as a platform, as an open source platform, assumes the programmability and versatility advantages about open source platform, and is interesting for calibration automation and for processing in the speed of processing and real-time modeling. For future research, we want to try to examine the relationship between camera characteristics and model quality, and explore reconstruction quality in relation to calibration techniques and pre-processing tools, including in-app processing, to have the possibility to people to acquire directly from one cultural heritage that someone could love and want to digitalize, and have this in-app processing that could be inside the whole box for all this cultural heritage. And thank you for your kind access.
Thank you, Cristina. Does anyone make a question? Okay. Cristina, did you have any difficulties in using MICMAC, because Cloud Compare or other software are commercial software, are probably easy to use, and so MICMAC, please would you tell us something?
For sure, commercial software are simpler to use and also maybe have times that are very cheap in confront with programming with open source software. But with Micmac, we have the possibility to manage all things, not in black box. And now Micmac for times was not so was this vast usage because they hadn't an user-friendly interface. But now the last year was created a very user-friendly interface that is integrated with the possibility to write the code in the interface. So it could be a possibility also for not expert user of coding to use that and without not so much problems.
Okay, thank you. We can continue. Thank you, Cristina. We can continue with Alessandra Capolupo, the next author. Alessandra and me, Eufemia Tarantino. We worked on remote sensing data. The title of the paper is Landsat 9 Satellite Images Potentiality in Extracting Land Cover Classes in a GEE Environment, Google Earth Engine, using an index-based approach, the case study of Savona City. You can start, Alessandra.
Thank you very much for introducing me, and good morning, everyone. Today, I'm going to illustrate the findings of our research concerning the analysis of the potentialities of a Landsat 9 platform in extracting land use and cover maps. This is more because actually we know that the information concerning land use and cover are essential to understand the role of our Earth, but also to analyze, to foresee the changes in the next future. So for that reason, we need a platform that gives us a continuous stream of data that are able to, that give us the possibility to analyze the history of our Earth. And Landsat mission gives us this opportunity, since actually it was launched for the first time in the 1970s. And Landsat 9 was the last launched platform, and it was in continuity with the Landsat 8 in order to give the possibility to continue the mission of Landsat 8. So, which is the main problem of this kind of data, that we are, in most of the cases, processing big data that exceed the storage capacity of our system. And for that reason, actually, we are not using anymore the traditional computer system to analyze them, but we are more devoted to use cloud-based platform as Google Earth Engine, that is a cloud-based platform released by Google in 2007. Why this platform is so popular in the last few times? Just because actually it is characterized by an interactive application programming interface that gives the user the possibility to customize and develop their own code in Python or JavaScript. But also because actually we can use different processors that can work in parallel and so speed up the procedure. And lastly, one of the more important characteristics that it has is related to the possibility to use the data catalog that is integrated, and it gives the possibility to just to consult just one catalog and to access to all the free available vector and raster data. But at the same time, we know that, of course, this kind of platform has some difficulties because it isn't characterized by a user-friendly interface, and so you have to have some IT skills. So, which is the main aim of this study? We want just to understand the potentialities of a Landsat 9 platform in extracting the land cover and land use map. And to meet such purpose, we decided to apply an index-based approach just because we know that is one of the most popular, since it gives the possibility to extract quickly, to extract land cover classes quickly, having if you want to analyze it to obtain the land use maps of an interior region, actually you have to apply it to combine more indices together. And lastly, we also evaluated the performance of the indices that we applied by using a statistical approach. The pilot site was Savona, that was selected because of the complexity, its morphological complexity. And so we consulted the data catalog, and we considered all the data from the November 2021 up to November 2022. And we filtered all these data according to some criteria like the study area, but also the cloud cover percentage. Indeed, we fixed the threshold of the cloud cover percentage at the 30%. And after that, we found that just one image was as some that was satisfactory to meet our purpose, and so we started to pre-process it by applying an atmospheric correction, but also using performing a georeferencing, and at the end we also performed the pan-sharpening approach in order to improve its accuracy by using the same algorithm of Landsat 8. The resulting images were used to compute two different indices, NDY and sub2, that were used because they are particularly relevant to extract vegetation information, but according to the literature, actually they give the possibility to extract 4 classes: water, built up, and dense and sparse vegetation with a different accuracy in accordance to the purpose they were developed to. Indeed, albeit they are using the same spectral bands, actually NDY is more connected to the plant phenology Instead, and sub2 is more used to extract information concerning the biomass, because it is able to minimize the soil spectral signature, and for that reason, we can also use to extract information about the discontinuous vegetated areas. So what we see that both qualitatively and quantitatively point of view, we can see that in accordance to the literature, these two indices extract 4 classes: built up, water, dense, sparse vegetation. And we can also notice that the amount of pixels that belong to water and built ups were absolutely the same. In contrast, we cannot say the same for sparse and dense vegetation, and it is mainly due to the purpose of the index, because the former is related to the plant phenology, and the second one is saying to the possibility to extract also information regarding the discontinuous vegetation. And of course, this reflects on also on the accuracy. Indeed, the NDY has a good accuracy, but is a medium because it is around the 80%. We say the M72 is around the 90%, so is more accurate. So what we can conclude that for sure Landsat 9 is in continuity with the Landsat 8, because it is the same spectral and spatial resolution of the Landsat 8, but we can find some difference according to the radiometric resolution, because in the Landsat 8 has 12 radiometric bits, instead the other just 14. Both indices, of course, shows consistent results, and the N72 were more accurate. So the overall accuracy that we found, as well as also the producer and the user accuracy, were aligned with the accuracy of the Lancet 8, and so with the findings that we found in literature. And for sure, cloud-based platform was a plus, since it gives us the possibility to speed up the procedure, both from the operational point of view, but also from the gathering of the images gathering point of view. So thank you for your attention.
Alessandra? Is there anyone have a question? No? I would like to ask you, why did you choose Savona?
Okay, actually for two reasons. One, the former, because actually we wanted a region that was characterized by a complex geomorphological environment, because it is on the coast, but is also characterized by a mountainous surrounding. But there is also a technical motivation, because actually the Lancet 9 was launched in 2021, and so for that reason we cannot access to a lot of images, and in particular most of them were not calibrated correctly. So there is a problem regarding in this period.
Okay. Thank you, Alessandra. Okay. We can continue, we can end this session with Carlo Barletta. He's online, I hope. Carlo Barletta, Alessandra Capolupo, and me, Raffaele Tarantino, we wrote a paper with the title Integration of Copernicus Data and Services to Assess Local Aridity Conditions in the Apulia context, the case of Marina di Ginosa. Carlo, if you... Yes. Okay, you can start, Carlo.
Okay, thank you for the presentation. Good morning, everyone. I'm Carlo Barletta, and I'm going to present the results of our study entitled Integration of Copernicus Data and Services to Assess Local Aridity Conditions in the Apulian context, the case of Marina di Ginosa. Nowadays, the Copernicus program of the European Union is a significant source of data and information for environmental analysis and monitoring. Its free and open data are provided by 6 thematic services, including the Land Monitoring Service and the Climate Change Service, and are acquired by in situ measurements or by a constellation of satellites called Sentinels. These data today allow to address many global issues, such as that of water scarcity. Climate change, which could result in changes in precipitation and temperature, is expected to affect in the near future the water availability for human consumption and ecosystems, leading to possible changes in the hydrological cycle and therefore affecting the soil-water dynamics, which depend, among other things, on climatic conditions. As a consequence, this could lead to drier conditions than in the past, especially in critical areas of southern Europe, as concerns the natural water availability, such as the Apulia region in southern Italy. In order to analyze and handle a large volume of geospatial and Earth observation data, Google developed the Google Earth Engine platform, which is a free-to-use cloud environment which uses Google's high-performance computing capabilities. In its code editor, it is possible to write and implement algorithms written in a JavaScript programming language. Developing new tools is important to improve the resilience to climate change. Recently, ISPRA, the Italian National Institute for Environmental Protection and Research, developed for the Italian territory the Big Bang procedure for the monthly evaluation of the main water balance components with a geometric resolution of 1 kilometer. The aim of this study is to integrate different free and open data provided by the Copernicus program of the European Union and other data from other institutions to retrieve locally the main water balance components as defined by the ISPRA Big Bang procedure, and to assess also local aridity conditions. To meet this purpose, a specific JavaScript code was created in Google Earth Engine environment. The territory of a basin, including the locality of Marina di Ginosa and characterized by a Mediterranean climate, was selected as a study area. In this slide are reported the main open data used in this study, the available water capacity map from the European Soil Data Center, the hydrogeological complexes map provided by ISPRA, the mean monthly observations of precipitation and temperature from the Climatic Research Unit, which is a data source of the Copernicus Climate Change Service, the soil sealing maps with a 10 meters geometric resolution derived from Copernicus Land Monitoring Service imperviousness layer, the EU DEM, and the Corin Land Cover 2018 map, from which it is possible to see that the case study territory is mainly dedicated to agricultural use. Here is reported the workflow followed in this study. After entering in Google Earth Engine the precipitation and temperature data measured at the Marina di Ginosa meteorological station and the other input data, the main components of the water balance, which are the inflow, the actual evapotranspiration, the surface runoff, the groundwater recharge, and the variation in soil water content, were estimated for each month. The evaluation was carried out for 3 hydrological years, for October 2015 to September 2018. Lastly, the local aridity assessment was performed by calculating the FAO-UNEP aridity index. In this slide are reported as an example the annual mean maps of actual evapotranspiration, surface runoff, and groundwater recharge retrieved at a 10 meters resolution for the year 2016-2017. From these maps, it is possible to see the spatial variability of these components within the case study territory. Here there are the graphs of the annual water balance, from which it is possible to notice that the driest year was the 2017-2018, while the wettest was the 2015-2016, and the monthly water balance from which we can observe the high variability of precipitation for this area. Furthermore, according to the outcomes of this model, a large part of the inflow, the precipitation, is lost due to evapotranspiration, while the groundwater recharge is 0 for the years 2015-2016 and 2017-2018, while the runoff is about the 10% of the inflow. From the values of the variation in soil water content, it can be noticed that for all 3 years, the input, the precipitation, is approximately equal to the outputs, which are evapotranspiration, runoff, and groundwater recharge. Moreover, from the differences between the inflow and the evapotranspiration, we can observe the internal flow, from which highlight that the natural availability of the water resource for this area is very limited, excluding external contributions, and is minimum for the year 2017-2018. The applications of the FAO-UNEP aridity index instead showed that the climate type for this area is dry semi-arid, considering considering each year and for the whole period of analysis. In conclusion, the Google Earth Engine Cloud platform turned out to be optimal for the implementation of this model of precipitation temperature data for the Italian territory or for the southern Italy. So I decided to implement this study only for a small area, extending the data of Marina di Ginosa to the territory of the basin of the covering this area.
Thank you, Carlo. Thank you, the authors, for presenting their works. Thank you, everyone, for attending this workshop, and I hope to see you in the next ICCSA conference next year. Okay, bye-bye, everyone. Thank you.
No, io comincio di trovo. Tutti i giorni sì, ognuno di noi oggi sta poi ci pensiamo. Ho già l'indirizzo tutto. Mi sono già informato.
A che ora inizia la cena? 8:30. 8:30?
Però ora locale sempre. Cioè, no, sei fatto, no, io tra l'altro non ho il
Vabbè, no. Sì, sì.
Poi Andy, come vedete we are smart. Non perdersi un altro caffè? No, io sì. Io lo so. Lo so?
Dai, io prima ti accompagno. Poi io vado, se possibile. Ci vediamo stasera a cena.
Ah, vai, no.
Sì, perché Cristian non mi ha chiamato adesso. Ora sto prendendo lo scusi, sì, adesso scusa, non mi
Sì, no, mi dispiace perché sono una... No, mi dispiace tanto, scusate, essendo una conferenza scientifica col fuso orario ho fatto un po' di caos, perdonate. Penso stiate parlando delle domande guida, giusto? Seguendo le domande guida. No. Ok, allora cerco di essere brevissima. Sono Andrea Vittori, ricercatrice al Dipartimento di Architettura e Studi Urbani e in realtà mi sono in veste di delegata alla sostenibilità del polo del Mantova. Il tema, perché crediamo che il polo del Mantova credo sia un tema molto importante sul quale investire, in realtà tralasciando ciò che magari può essere stato fatto in passato, soprattutto grazie alle associazioni studentesche, o comunque assolvendo diciamo, tutto quello che era anche a livello di Ateneo, quindi calato sul polo di Mantova, il contributo che ci sentiamo di offrire, essendo un polo comunque di dimensioni ridotte, numero di studenti e di docenti ridotte, ci offriremo come caso studio, come un caso pilota nel quale magari implementare azioni che sono già state implementate magari in altri dipartimenti o nella sede centrale o in altri ruoli, in modo tale da sperimentare. Essendo più piccolini, chiaramente abbiamo più velocità magari di implementare le azioni. Chiaramente tutto questo sulla base di criticità riscontrate dal polo di Mantova, cioè ovviamente non è un one size fits all, ma è sulla base delle necessità concrete del polo. Quindi questo è un po' quello che giusto. Grazie.
I'm history. But
That's it.
it's so Thank you.
Salve.
Περιμένεις Βασιλική. Γιατί θα μου είπε θα κάτσει εδώ πέρα. Τώρα στη τυχαία θέλει κάποιον από εμάς. Πριν είχε μείνει άδειο το δωμάτιο. Γιατί έφυγε μία που ήρθε και ήρθε μετά η κοπέλα. Αλλά άμα είναι να μην έρθει η Βασιλική και να κάτσει έξω, να ξέρω να ζητήσω από κάποιον άλλον κάποια στιγμή να έρθει να κάνουμε rotation.
Someone has to be doing all that. You have to close it, so if you experience it, you go out. Just inform us to close it today.